else on the chat window in case you want to communicate. Right. Okay, so why do we need to learn assembly language? Okay, so if you look at the IDE, like the KEL or your STMQ, most of them nowadays have two windows that show C and the assembly side by side. Okay, so as much as possible, we try to program in C because it's more convenient. But the processor cannot execute C, so it will compile and it will run the machine code. So we compile from C to assembly, and then the machine actually goes one step further with, to execute the machine code. So you need to learn assembly and C to use the processor efficiently to analyze the code with precision. Okay, so let's say you have some very hard to explain bugs. So if you understand assembly, you will know exactly what's going on and to extract maximum performance. Okay, so here is the here is the difference between difference or comparison between C and assembly. So let's just look at the pros. Okay, because the cons are just the opposite. So C is easier to learn, more portable. That means you can transfer your code from Intel to ARM if necessary, and then you use C to handle complex data structures like maybe array or even higher than that, like linked list or tree structure. So all those very high level data structures are easier handled in C. But you also need to use assembly sometimes because you want it allows direct control for everything, and there's some instructions that this cannot do. There's some assembly language instructions that can do what C cannot do. For example, like turning off interrupts. Okay, that kind of instruction must be done in assembly. Okay, so if you are using Linux, you can install the GNU tools on Linux according to these instructions here, or you can also do it for Windows, and you can here no matter what you do, here is the steps that you take to get your program from C code to an actual program code. Okay, so this one is assuming that we have an ARM-based PC, okay, like Apple. Okay, for Intel, you will actually the path is the same, but you will get Intel machine language, and you can also use a GNU compiler to generate ARM code on Intel. So there is something that is possible, but you probably have to add some switches. Okay, so if you look at the command here, the command here is GCC. Okay, if you look at these are all in GNU commands. So if you are using IDE, you don't see this, but actually this is there in the background. Okay, so maybe I will right now I will just go ahead and run our simulator that I give the link. Okay, so actually I just found it last night. Simulator. Okay, so one see. You go to this website, and there's a few processors here. BIOS, which is for Altera. This is a soft copy, soft core processor, and then there's a MIPS processor, and there's the ARM. So for the ARM, there's only 3 platforms here: the generic ARM, and the one that is on board the Cyclone FPGA from Altera/Intel. So these two are the same instruction set, but the SoC version has peripherals that you may want to can experiment with. Okay, so just go here and then I go. And loading. So the good thing about this simulator or emulator is that you don't need to install anything. Okay, so actually I can do C coding, but I don't know how. Here, yeah, you can do something here. But anyway, if I want to run something, I will compile. So or I will assemble this. Yeah, this compile button. Okay, so this program is blank, so nothing there. So I can get sample programs like that, and it will immediately assemble and compile or assemble. Okay, so this is the editor, but it's not so useful. There's nothing there. So audio output test. Okay, so this test actually doesn't work. It doesn't have any meaning on STM32 because this simulator is for the DE1 FPGA. But you can go to the editor here. Okay, this is the code, and then this is this assembly. So you can scroll back. Let me check. Where is the starting address? Starting address is should be somewhere here. I will just what I can do is just compile and load. So what you see at the bottom there is the command to compile and load. Okay. So here it is an IDE, but actually it's executing the code. It's executing the compiler, and then it links. So this is the one that I wanted to discuss just now. Okay, so the compiler here is not GCC, but it's -Altera-EABI-AS. So that's the full name of the command. You probably can find this somewhere on the internet. Then there's a lot of switches here. Okay, there's this something with the minus here is called a switch, and minus something. Okay, like minus mfloat-ABI equals soft. And then, for example, here this processor here is Cortex A9. So minus M CPU Cortex A9. So the code will be compile or assemble into Cortex A9. Okay, and then I saw C yesterday, but I couldn't find it. But it doesn't matter. Okay, we're not learning C today for now. So you can go to the editor, edit this program, and then recompile. So, for example, if I want to change something, I can just change something from the sample code, and then I can disassemble. So right now, I'm not sure why the disassembly is not showing the address that I want. Maybe I should go to start. Okay, start is 0. So if I assemble, and assemble from address 0, I should get something there. Somehow it's gone. Okay, so yeah, what I want is actually to like get what is the assembly what is the machine language for this move R8 pound 48. Okay, so let's try to trick it to something else. VG8 test, for example. Okay, this is a different machine language, and then still I cannot trace where is it. Okay, this is location 0. Okay, not going there. Scroll and find the address 0. It's address 0. Here. Okay, finally found it. Okay, so we should look, we should start from here. Okay. Address 0, we have move SP something. Okay, so that one was here. Okay, move. See the machine language, the assembly language says LDR SP equal 8 followed by 5 zeros. Okay, when you disassemble, it converts that to move SP pound 838868008. Okay, so that is the same number, but now here is in decimal. Okay, so when you assemble, you use LDR and equal, but the assembler converts that to move. Okay, because that's the most appropriate for this instruction. Remember that the LDR may sometimes get converted to some other machine language. So LDR is like a pseudo or a meta operation, okay, or meta opcode. It is when you write your code, you just say LDR, but sometimes it gets changed to something else. Okay, so here the second instruction is LDR R8 with a number. Okay, you can see here on the second line here we have LDR R8 PC pound 172. Where did this come from? Okay, it's because this value cannot be loaded at once. Okay, I think I mentioned yesterday. Okay, so if the value is small enough, then the assembler can use a single move. Okay, like the move SP here, it gets converted to a single move. But for this value 332211F0, which is a big number, so you cannot copy or you cannot copy this value directly into R8 in a single step. So what the system does is that it will put this data somewhere in literal pool. Should be somewhere down here. Okay, somewhere down here. Okay, cannot see it. And based from calculation, okay, to get there, you need to take the PC and add 172. So we'll get the value from down in the code. Okay, so because it's relative to PC, that means it's not that far away. It's just down in the program. And then the third instruction is move R9 R0. So this is the disassembly. Okay, from address, basically from address 008, we have the opcode E1 A09000. Okay, so the disassembler try to convert that, see if it works. Okay, so it's the same as the one that we entered before. And then how about let's go to look at a few more. Okay, so for line 17 we have move R0 to R8. Okay, so it's the same thing. The disassembler disassembles the assemble machine code to the same thing. But if you look at the fifth instruction here, okay, line 18, we see BL field color. That means we are trying to go to a subroutine called field color. And the field color is here, if you look at the label on the left here, field color is actually 54. Okay, so 54 is, you can check down here. Here it is somewhere here. Okay. 54 is address 54. Oh, okay, you cannot see this. This is source code. Okay. 54 here means 54 in machine language. In this part here. Okay. So BL54 is actually down here. Okay. Okay, this is 54. So when you say BL field color, it will jump to this address 54 and do a few instructions there. Finally, at the end of this field color subroutine, we see the BXLR down here. So this is the end of the field color subroutine. Okay, and then what else? You have ROR, R8, 31 times. So actually there is a rotate left 1 bit. Remember that you cannot rotate left, but you can only rotate right. So if you rotate right, there's a big number here. Actually is 32 minus 31. Okay, so subtract 31 from 32. So you actually shifting left by 1 bit. So anyway, that instruction got assembled, and then it gets converted to E1A008FE8. So this is the machine language, and from this machine language, the disassembler disassembles it back to the same instruction. Okay, so the point I'm trying to say is that when you assemble, it becomes machine language, and then when it disassembles, sometimes it becomes something else, like LDR here, obviously. Okay, you get something else 2 different times. Okay, this the same LDR instruction, but first one is move, the second one is load, and then the BL field color, you put in a label there, but in the actual machine language, it is replaced with a number. Okay, and then this number 54 is actually that is the actual number that the processor uses. But here somehow the disassembler can attach 54 is actually field color. So you're going to field color. Okay, so the other one is I want to use the other one I'm trying to show here is that when you assemble or compile a program, so there is a program that is running in the background, and the IDE is just an interface to you. So you can actually run the program here if it's available on your hard disk, okay? And you can compile using this code. But since this is a web base, so this program called the something AS is the assembler. So this assembler is actually inside the server that hosts this simulator. Okay, so if you are do it on Linux, then you find GCC code, and you can compile it to you can compile C to assembler only. Okay, so for example here I can have program.c, and I can compile just to assembler only and stop. Okay, so the way I do that is I give the command. Okay, you can see this dot to dot, right? From the first green dot to the second green dot. I give the command gcc -s. The -s here is to produce assembly code from C source. And then I give the output file name -o program.s. So .s is the default file extension for assembly code. And then last is the file name that you want to process. So program C is proc.c is the file that I'm going to compile. Okay. Or I can also after that I can compile it to make binary code. So from the proc S, I can continue, okay, from the half resume from halfway, right? Because right now I already have the proc.s. So I can continue by giving the same command gcc, but now I give the name -o proc. So that means the output is called just proc, no extension. And then the input file name is proc.s. So GCC knows that if the extension is .s, it is an assembler file. Then .c is a C code, so it knows what kind of thing they have to do. So if it's a C code, it compiles it. If it's a assembler code, it will assemble it. Okay. Or I can also do these 2 steps in one. So I can do GCC -o proc. So output of the process is called proc, and the input is proc.c. So I will go actually 3 steps, right? From proc.s to proc.s. This one is not saved. It's inside system. It's not shown. And then also I can get the proc.o if I want, but it's also not generated. And I will end up with just proc. Okay, so in Linux, there's no .exe like in Windows. But if you're doing this in Windows, you probably need to put proc.exe. And this is the executable. So in Linux, when you want to execute a code you do dot/prop. Okay, later I will try to access my Apple iMac. So and then from there I can show you this thing works in Apple because Apple uses ARM. But Apple, of course, uses a 64-bit architecture. So I need to have a switch there to tell it to compile to 32-bit. Okay, so anyway, there's many switches. I'm only using a few. So minus big S produce assembly code from C. Minus O is the output file name. Output file name follows, and then the last one is the input file name. And then minus big O is a switch to optimize the code a bit, and then there's a minus O3, so maximum optimization. So you might not want to optimize too much because when you're learning, you don't want you want to learn. So if you optimize too much, things get lost because the compiler or the assembler will remove some instructions. Okay, so you can use if you install this in Linux, okay, and you want to write your own code, then you will use a nano editor because this is the simplest editor and still usable. Okay, there are even simpler editors on Linux, but some of them are not terribly user hostile. Okay, like V. Okay, VI to me is really hostile. Nano is not so bad. So use Nano to create your file, and then here is the code. Okay, so see this code. Now, if we have the simulator, we can actually enter this code. So let's do this here. Okay, so let's create a new file. Okay, so we need to have, actually we don't need the text, right? Can I try delete everything? Okay, so dot text dot global main, which is the main program, then dot function main, it's a label, and then I move put 2 into R0 and wait from the thing, better to put everything aligned like that. Okay, and here if on Linux you will compile it to make it something that you can run, but over in the simulator, but easy, just compile and load. So it will compile it into machine language. So move R2 pound 2 becomes E3 A00002. That's the machine language, and then VXSR is the next instruction. Okay, now there's also some other instructions down here. Okay, but this actually comes from the garbage that we have just now. Okay, because just now we had we loaded a program, and that program just now put something in the memory, so that data was not erased. So you have to ignore. Okay? So this instructions, the disassembler doesn't know it's not our program, so it will just disassemble like that. Okay, now we have this program, we can run it. Okay, so what you do is we try to put the PC first. Check. Okay, PC is 0. Okay, so PC is 0. That means if I step, I should execute this instruction, and the result is to put number 2 in R0. So let's just step once. See this? R0 becomes 2. So this simulator is not bad, even though I just found it last night. Okay, and then I see the BXLR. So this one is actually useless because I didn't put anything in LR. But if I keep on doing this, if I just do this, it will copy LR, which is 0, and put it back to PC. So if I do step, our PC will go back to 0. So if I keep on doing this, this is an infinite loop. Okay, because BXLR actually what it does is to load PC with LR, and LR contains 0. So it's keeps on doing that continuously. So anyway, this wanted to note is that this disassembler or this simulator is for the A series processor, but many of the instructions that you need to learn can be handled by this simulator. So it's good enough. Okay, for me, it's good enough because we want to learn move, we want to review add, we want to see what load and store and so those things, simple things. Okay, so we're not going to run this as an embedded system. So that's okay. So this simulator is good enough to learn machine language. So the running here we will skip lah. Okay. So now let's say we want to display hello world. Okay, I don't think this works. Okay, I don't think this works in that simulator just now because it doesn't have a print statement or a print cannot handle print. It doesn't have the print subroutine. So, but let's say you have a C code that has a single statement print F and then hello world. Okay, so before it goes to print, it will load the necessary parameters. Okay, so we see here this push IPLR and then LDR R0 message. So these two instructions, they are there to so that you can pass a function to the printf, and then we jump to the actual print function, and then before we terminate, we reset the stack. Okay, so in C you just say okay, print hello world, but in assembly you have something that you have to prepare the parameter, call the function, and then reset the parameter, reset the stack. Yeah, this is the place. Okay, now let's try C code. Okay. Let's compile. All right. So this is the C code that was generated by the C program. That's the assembly language generated by this C program. Okay. So see a lot of trash here. Okay, so many things there. But there are from this noise we have to find the signal, right? So actually I cannot find printf. Let's check the symbol. Okay, printf is not here. Yeah, this is not really useful, but you can see the problem is there's so many things there. So let's try a simpler one. Okay, just make a simple function. Okay, so here I want to here. To do is x plus y, and here integer a. Very simple thing. Okay. Add 1. Let's see what happens when we have a function and what C does when it tries to call a function. Compile and load. And let's find out where is table. Get the symbol. Add is to find where is the subroutine. Okay, main is at section 23C. So I have to go down here. Okay. The reason there's so much there is because when you have C code, there's something called the setup. Okay, so you cannot just suddenly run C code. There's a lot of preparation that needs to be done before you run C code. So finally, we go to the actual main program. Okay, so the main program is 234, I think. Here, this one. Okay. Yep. Okay. So the main here. Okay, the main program just now is from here to here. Okay. From this move. From this move. Okay, from this move. Okay, from this 23C. Okay, to the VXLR. Okay, so basically, in if you're running a C code, the C code itself is a subroutine. So that's why at the end of the C program, there is a VXLR because it tries to go back to the operating system. Okay. Now that we know that main program is actually a subroutine, so and we know that the subroutine, the main program is in this our example is executing or is going to add. Okay, so let's see here. Okay, so the main calls add. So inside this main program, we've tried to find if there's any code here that goes to the add function. Okay, the add function here is at 234. Okay, so you can sort of scroll through, see if you can find it. Maybe yes, maybe not. Because this is not, this is it has a lot of garbage there. Actually, I cannot find it. This is the main, okay, but where is the function call? Line 7 is a equal add, okay. I think what it has done was to optimize everything, okay, because that's the problem with optimization. Okay, let's check the warning here. Variable A set but not used. Maybe that's a problem. That's a problem. Okay. Okay. I did set it, so should not be a problem here. Okay, this is the problem. This warning doesn't make sense. Okay. Oh, okay. Yeah, I set it to A, but I didn't do anything with it. Okay, that's all. Okay. So I just say A add, and then I think what it does is to throw away this whole thing. Okay. The whole function call is removed because I'm not using A. So let's do something with A, maybe print or something. And that's the problem with optimizers. It remove everything that is not relevant. Okay, since I do something with I set A with something, but I didn't use it, so it just throw away everything. So this one, no problem. Okay, I think less of a problem. And let's find the main again. So to find the symbol, find the main. Should be here. 23C again. Okay, 23C. So scroll to 23C. So that is the entry point to this program. Now there's something. Okay. Now it is calling the add function because it knows you have to calculate before you can print. Maybe not. It's also optimized away. Okay. It knows the assembler already calculate the result here and remove everything. So in the main, let's just print, not even a function call. So it knows the value is a constant. Okay, 1 plus 2 is 3. So they just put 3 here. Okay, see this? Move 3. Okay, it's already calculated the result. Move 3, and then move the string. Okay, that's okay. So that is what happened when you optimize. And I don't know how to turn off the optimizer. Okay, remember here, see, if you print this, actually you print 3. So here A is 3, and there's 2 parameters. So the first parameter is 3. The second parameter is the string. So the first parameter 3 is put into R1. Actually, second should be second. It's on the right. Okay, so the 3 is put into R1, and then the address of the printf is loaded into R0. The string itself is loaded into R0, and then it goes to the printf. Okay, you remember yesterday I said move W and move T is a better way to load addresses. So this number AF300000 is the string itself. So somewhere down here, there is the string. Okay, have to trace it, but somewhere there is in the literal pool. Okay, so with some difficulty, not much. Okay, you can try to learn what C code looks like in assembler. Okay, which is the point of this topic today. Okay, so you can see that when you optimize to the highest level, even functions get removed. Because if the compiler sees that the point of the function is to calculate a number and the number is a constant, it calculated the number beforehand and just print the number. So if you can, try to run this version in Linux where you can do a finer control, okay, like you can set the optimization level and so on. Okay, so here you can set the optimization level to highest, -03, or leave it out, no optimization, or -O only. So I mean intermediate optimization. So you can get 3 versions of the same assembly code from the same C program. Okay, same C program, but you can get 3 different versions of assembly language. Or you can also because you optimize it at a different level. Okay, or you can also write C and then compile it to assembly, and you can write your program in pure assembly, and also you can write the program in C and apply the highest optimization, okay, this is the one that is done by the emulator just now. So what optimization do is to simplify operation, remove dead code, okay, so or remove unnecessary code actually, and it will use register instead of memory. So by optimizing, you are actually making the code look different than C. Okay, from C looks like very complex, but when you compile it and assemble it and later optimize it, suddenly a lot of the instructions get removed, and the program is shorter. And also here we can see if previously we use memory to store a variable, for example, it may use a register instead of memory, and sometimes if it's a constant, if it gets computed constant, it totally remove the need for register or memory. Okay, so optimization often get in the way of understanding what the code does. So that's why we need to be able to control the optimization. Okay, so what's the point of all this? Okay, the point is you want to use C for most of your work, but sometimes you want to use assembler. So you have to know how C code communicates with assembler routines. So, for example, here is a program. Okay, that here is that program again. Okay, so in C you can see it changed to LDR R0 equal message, because we want to point R0 to the message itself, and then it goes to the print function. But even the LDR get optimized further. It change to move T and move W. Yes. So I think I confused you further. Maybe. So if there's any question, you should ask now. Okay. All right. So now we go to using a combination of assembly language instructions to perform things that could have been done in C. Okay. So for example, if I want to do if in C, you will just think in the straightaway logic. Okay, so for example, you have say x equal to 10, and then if x greater than 0, increment it. So at the end of this code sequence, x should be 11. So in assembly, if there's a variable there, there's a single variable there, you will use R0, because that's the default value, and then it will compare R0 to 0, okay, because we are doing a comparison here, and there's a branch. Okay, whenever you have an if, there's a branch there, and wait, this is a plus, not a plus, and this is minus or a plus. So if a branch is required, then it will skip the subtract instruction. So in C, you use greater than, but in assembler you will use branch less or equal. So let's try this on the simulator. So to remove this, okay. Just remember that the printf is there for dummy, okay, so that they will not optimize everything. It will probably optimize it. But let's see what happens. Okay. So integer x equal to 10, and if x equal to 0, x equal x minus 1, and print x. Okay. I'm going to predict that it will immediately calculate 9 there. It will calculate and it will just load 9. Okay. So let's compile this. And then I think the code here was step just once. Okay. Step to start. Okay, it goes to try to run this code. Should go to PC 234 or something. No. Better just go here and look for the main program. Okay, the main is at 234. Okay, just go to 234. Don't want to go to all that. Okay. Yeah, x expected. So all this code, okay, x equal to 10, if x greater than 0, subtract 1, it already calculated to be 9, and then they just put 9 in R1 because that is the second parameter before you go to the subroutine, and then it loads R0 with the address of printf and or the message. Okay, this is not the address of the message R0, and then it branches. Let me see. Can I can I turn off the optimization or not? Probably not. It's the only thing I can set. So whatever. Okay. Anyway, yeah. If you have C code, you need to be able to convert to assembler like this. Okay. So this is for the simple if, and here are some examples where I convert from equal and not equal. So if I say, okay, if A equal to 5, B equal to 3, so normally the first variable that the compiler sees will become R0, the second one become R1. So here A will be in R0, and then we compare R0 with number 5. And if equal, put 3 to B, or move R1 with 3. So if not equal, then you skip. So that's why you need to have a BNE instruction here. Okay, equal, here not equal. And here I have equal. Okay, so I want to check whether A is equal to 0. So compare R0 with 0. And if not equal, skip. Or if not equal, do this. So that means not if equal, skip. Here I have if A equal to B, do this. So I need to think about how to skip. Okay, so if A equal to B, do it. If not equal, skip. And because this is to check whether two things are equal, you can use TEQ instead of compare. You can use compare, but for equality, better to use TEQ. And then since this is divided by 2, okay, the compiler will convert that to shift right. And let's say you do if A, so that means if A equal not 0, right? So if A is anything that is not 0, so anything not 0, if A, if just A, that means it's the same as if A not equal to 0. Okay? So when you compare first, compare R0 with 0. And here if equal, okay, so here's somewhere. Then if you don't skip, then increment B by 1. So here we just say here we have more examples. Okay. Now here we want to check whether A is odd. So to know whether something is odd, you just check the last bit. Okay. So for example, number 1, number 3, number 5. If you look at the pattern, the last bit is 1. So to check whether the last bit is 1, you do test. And if odd, or if it's equal to 1, let's skip. Wait a minute. If equal, that means if equal, that means it's 0 actually. So if the last bit is 0, so the LSB here is 0, skip. Here you will execute this if the LSB is 1 or odd. Okay, so here b equal to 3 and p should be 1 here, right? R1. Okay, I put there. And then I increment c by 2, so I add R2, R2, which can be simplified to just like this. Okay, just add R2, PAM2. Both will be acceptable. And then here convert something from lowercase to uppercase. So first check whether it's lowercase. If for other combinations, don't do anything. So you must check whether the data is between small a to small z. So compare with character A. If it's less than A in ASCII, so skip. And then compare with Z, greater than Z, skip also. If you do not skip both times, then the character is between A and Z, inclusive. So then you subtract hexadecimal. So what? Okay, this is lowercase to uppercase. What if you? Okay, one more. Complete absolute value. So complete absolute value is if A is less than 0, negate or convert from negative to positive or takes the 2's complement. So here we compare negative. So basically is 0 minus R0. Okay, 0 minus R0. So if it's positive, then it's already positive. Okay, so don't do anything. Okay, what happens is that when you do 0 minus something and R0 is negative, if negative, then the result will become positive, right? 0 minus x, and x is negative, so the result will be positive. So it's already positive, so you skip, you don't do anything. But if it is negative, you will not branch, you will execute the RSB. And what the RSB does is to 0 minus R0. You will do the 0 minus R0 again, actually. But now, if R0 is negative, originally, then the new R0 will be positive. So in C, actually, you can just do something like this, okay, in one line. So you can say A less than 0, question mark. Then if it's already less than, if it's less than 0, that means it's negative. So you give minus A to A. Otherwise, just don't do anything. So it can also be done that way, but maybe it's a bit cryptic. It's just an option. Okay, so the last example here, convert uppercase to lowercase. So we know that in ASCII, the difference between uppercase and lowercase is 20. So to do it in C, it will become like this. If the character, the variable A is greater than or equal to capital A, and the variable A is less than or equal to capital Z, you will add 20. You can also do this in C. So here, what you do in assembly is compare R0 A less than A, we skip. Then if higher than that, you compare again. Here we do BG. If greater than Z, then keep it. Otherwise, it is something that you need to convert, right? So convert uppercase to lowercase means that you have to add. So here we just add 0, 0, 20. Okay, moving on. For the if else, we can have a, for example, for this example, we want to find the maximum. Okay, so the bigger of A and B will be copied to max. So first we compare R1 and R2. So if R1 less than R2, that means if R1 is less than R2, we go to the else. Okay, so we go here. Okay, so here is the case where R2 is the max, because R1 less than R2. Otherwise, then you drop here. So if you arrive here, that means R1 is greater than or equal to R2. So you want R1 into R0. So here we put R1 to R0, and on the alternative route we put R2 to R0. Right, so a few examples here. Find maximum again. Okay, so same thing here actually, right? Same thing, but here we use the ternary operator. Right, and here for the second example, we have if A minus B less than 3. So you have to subtract first and then compare with 3. And if true, you want C become B times 3. So this is how you multiply by 3. Okay. So what we have here is that we have R1 logical shift left 1. So this part is actually 2R1 add with R1. So R2 equal R1 plus 2R1. So this is 3R1. Else you want B times 5. So you multiply by 5 without using multiplication, which is expensive. Okay, multiplication is a computationally extensive operation that you try to avoid. So here we do this. R2 equal R1 plus 4. Because when you shift left by 1, you're actually multiplying by 4, and then you add 1. So this is 5, 1. Let's see whether we can get something like this in our simulator here. So we have to fake something. We have to put an input there. Okay, so that it doesn't optimize it. Okay, so I will scan here. Yeah, and then so y equal x times 5. And we want to print y. We want to use y so that it will compute and not skip anything. So let's compile this. Compile fail. Okay. Okay, so let's go to line. Same address again. Okay, here. Okay. So we have see this line. Add R1, 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 LS, L2. So it's using the same location for the destination, which is okay, but there's the R1, 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 LS, L2. That is the multiplication by 5. So what I just did is to prove to you that whenever it can, the compiler will try to avoid using multiplication, actual multiplication instruction. Okay, let's try some crazy number that is very hard for it to optimize away. For example, like 101, for example. Let's see what happens. Will it still use multiply or something? Okay, 101 is, yeah, it cannot optimize away. Okay, so here you can see that it loads 101 to R1, and then there's some manipulation, and then there's a multiplication somewhere down there. Okay, how about times 3? Okay, which was the original one of the original ones. Okay, times 3. Compile this. Okay, times 3, we should see somewhere in the code LSL somewhere. Okay, here it is. Okay, so this is times 3. Right, so that's the point, right? This software looks complicated, and there's a lot of instructions there. So I just showed you where to look. So you go scroll and then find out what is the relevant instruction. So here we can see I've proven that if I do times 3, it will do LSL1 somewhere inside the code, and then times 5, it will do LSL2. And then let's say I compare something like this, right? This is to convert a binary to ASCII to a binary. So if it is greater than 9, subtract this value. If it's else, it subtract another value. So here we use a trick here actually, right? So if basically this is a ASCII to binary, meaning that let's say I have ASCII 8. Okay. 8 is actually 4, and I want to convert this to 1010. So that is the question here. Okay. And if it is a digit, if for example is 9, right? It's actually 39. So for 39, I can just subtract 30. So this one, 39 in hexadecimal should be 1001 in binary. Okay, so the ASCII can be ASCII 0 up to ASCII 9, and then ASCII A to ASCII F. The output of this operation is either 0000 to 1001 for the digit for the numeric ASCII, and for the alphabetical ASCII it's 1010 to 1. So you have to subtract a certain value, okay, and that value is determined by the offset. Okay, so we calculated here. And study the code afterwards, right? Or you can also do the reverse. Okay, so for example, from 0, I want to make ASCII 0. So I just add from 0 to 9. So the range is from 0 to 9. So anytime can convert it from 0 to 9, or it's a number. So add this ASCII 0. So this is actually 0x30. If it is 1010 and above, so you have to add a bigger number. So this is the number that you have to add. Okay, you have to add this, and then you have to subtract from the offset. Okay, then after if you should have the while construct. This is for looping. So when you are looping, you can count up. Okay, this one is a count up. So for example, you want to count 1 plus 2 plus 3 plus 4 plus 5. So prepare the result first. Okay, this is the sum. Sum is there, and then this is the counter. So you compare the counter. Wait a minute, this is reversed. I have to swap this. This is the count. This is the counter, because this is the up counter. And then this is the sum, I think. Because the sum is 1 plus 2. So it starts with 1. So it's actually not the same exact, not the exact same code with the C code. So first you compare whether you have reached count of 5. Okay, here you compare this first, and if not, we add we increment the sum. Okay, so that should be this one. Okay, and then we increment the counter. So this one. I think I got this code. Not a good example. The variables are mixed up. I can skip that one. Okay, maybe I should fix it now. Okay, let's try to delete all this. Okay, sum starts from 1, and the counter also starts from 1. Okay, so let's assume this is the sum, and then the loop is controlled by the counter. The counter is this one. Okay, so you have to check the counter because that is how you control the loop. So you should check R1 here. And then the sum is in R0. So you are adding the counter. So if the counter is 1, you also add R1. So this is okay. So this line, this add actually performs this line. Okay. And then the add R1 actually increments the counter here. So this is the I. And then we branch. Okay, yeah. Only this is the typo. Okay, throwing away everything. Only one typo there. We should compare the counter, and the counter is R1. So I need to fix this. All right. Okay, this is something that you were doing just now. Okay, population count or counting the number of bits that are 1. There's many ways to do this, and this is only one way. So that's analyze the population count algorithm for a long time. There's many ways to do it. There's a fast way and a simple way. And simple way normally is slow. Okay, so this method, what it's doing is, how it does it, takes X, which is the data itself. So 5555 should contain 0101 4 times, right? So 0101 contains 2 bits, 2 ones, and then multiply that by 4, you should get 8 from this 16-bit word. And then the count is in C. So this code, what it does is that it checks whether the data here has 0 or not. If the data is 0, terminate. Otherwise, shift the data by 1 once. Okay, and if the LSB is 1, increment the count. So if your data is something like this, okay, and you do this x, this is x, if x equal 1, okay, if x and 1, okay, x and 1, you should get 1. You should get true. This is how you check whether the bit is set or not. So the result is true. That's all you need to know. Okay, x n1, okay, x n1, this is x, this is 1. If you end these two, you get something that is not 0. So if it's not 0, that means this last bit is 1. So you increment the counter. So that's what it does. Okay. And then what you do next is you shift everything to the right. And you have to make sure this is actually unsigned. Okay, this is a mistake here. Cannot be, must be unsigned. Yes, another place I need to make some correction. Okay, so it must be unsigned because if it's signed, then you possibly can insert 0 or 1 from the left. So you don't want that. You want to always ensure 0 is shifted into the left input. So if you shift this, this is data. You shift this once, okay, so everything gets shifted once. So and then 0 comes from that. So you will get 0, 0, 0, 0. And when you check for the loop the next time, you can you will fail, okay, because now x is equal to 0, so it will terminate. So this is the test data in R1. Put the count in R0. So this is the x, the variable that you want to check. This is the counter, the count value of how many ones you have. And then here is the end. Okay, so here is the end. You do this end. Yep, another mistake here. I must have. Oh no, it's okay. Okay, I end this and I copy the bit to R2. Okay, so whatever value I have, okay, I can have only two possibilities. It's either 0, 0, 0, 0, 0, 0, 0, 1 or 0, 0, 0, 0, 0, 0, 0, 0. Okay, so the value that was that's the result of the end is into R2, and I just add R2. I don't need to use the carry, and I don't need to mess with the flags. Okay, the result is in R2 and edit. So so that's this part here. And then I shift right. Okay, so what I do is I do logical shift right, and I set the flag. So if after the shift the value is 0, then I don't need to loop. So if it's not equal to 0, continue. If it's 0 like this, then drop down. Okay, so if you do this in C, and let's check this. Okay, let's do this in our assembler, in our simulator here. Okay, so the algorithm is here. Okay, first, the counter is in Y. Set this to 0 first, and then 4. I can also do while, and then as long as x is not 0, I can just put x there. I don't need to put not equal to 0, and then inside the loop I shift x one time, and here I have if x n1 is not 0, I increment y, and then I have to make sure I print y so that it will not optimize away. Compile it, see what we get in assembly. Okay, jump to address 234, somewhere here. Okay, here you can see first it compare R3 with 0. Okay, compare the data. So the data looks like to be in R3, and then if it's already 0, skip, go to 268. which is to print the value, else do shift right, ASRS. It doesn't choose LSR because I put integer, and then you shift to the right, and then if it is not equal to 0, not equal to 0, go to 25, go back again. Okay, go back up. I don't see it. I don't see it adding the value of y. Let's go back here. Okay, one experiment. Let's change this to unsigned file. Just want to show you if we use unsigned, it will hopefully it will use LSR. So okay, here see this. Okay, LSR. Just now it was ASR because signed and unsigned produce different different shifts. Okay, but the counting is not yet done. Okay, so oh, okay, I put this. Okay. If I do that, then there's actually the loop is empty. Well, the loop is empty. Okay, so now let's fix that. That one fix. Okay. Okay, get the data from R3. Okay, R3 contains the count, and then sorry, R3 contains the data to be analyzed. R1 contains the count, and then test. Okay, basically you are doing AND with 1. Okay, remember that test is same as AND with 1. If not equal to 0, add 1. So, or in other words, if equal to 1, increment R1. And here we have the ADDNE mnemonic. This is applicable only to 32-bit ARM. This is conditional instruction, which I haven't mentioned. Okay, so you don't see compare, you don't see branch there. If the lambda is not equal, it will just add. This is one of the interesting characteristic of 32-bit ARM, which something you cannot do in Cortex actually. Okay, and then the less. Okay, so if one, add 1, and keep on shifting, and then repeat. Okay, repeat. So go back to 25C. So you only you quit from this loop when R3 is 0. Okay, so when R3 is 0, the branch is not taken. When R3 is not 0, branch is taken. So that's the BNA down. So model is almost the same, except that it uses TEQ. So yeah, this one I also can change this instead of N, I can say test or test TST, not in context. Okay, so I think the last one before our break is the do while instruction or the do while construct. Here we do the checking at the bottom. So do something first, and then at the bottom there, compare. So for example, you want to find the maximum of few numbers. Okay, so using a pointer, point to this location 2000, 2000.1000. Okay, so this is a big address, big number here, and then we want to find what is the biggest number in this block of words, and the number of words is 64. So what you do here first, you load the pointer with ptr, and then here is dot word 2000 or you can also do we've seen that this is converted to move w and move t. Okay, so may not be the same when you assemble. And then we set the maximum first. 0 is the answer. The biggest number inside this array is in R0. So you compare R0 with the current number, and the current number was loaded from memory using the LDR. So compare that. If then the R0 is already big, don't do anything, otherwise update. Okay. So compare R0 with R3. If R0 is bigger than R3, don't do anything, skip it. If R0 is smaller, then update or change R3, copy that to change R0 by copying the number from R3. And then we decrement the counter. Okay, the counter here is in R2. If the counter is not yet 0, repeat. Okay, so it will keep on looping there until the counter is 0. So if your number is 64, then it will loop 64 times. And when we finally terminate the loop, by that time R0 already contains the number that we want, which is the maximum, and we save it. So we save that to address max, which we can get by using the ADR function. Okay, so when you count up, it's less efficient because you must have the update and the compare and the branch. If you count down, you just need to subtract and okay, when you count down, you just subtract the counter and keep on looping until it's 0. Okay, so that's it for the simple branch. Later we go to the IT instruction, which is the advanced form of branch, and the stack. Okay, so let's take a 15-minute break. Okay, I'm back. I'm not going to wait until 11:30. There's a lot more slides to finish. Okay, so this section is about the IT instruction or the if-then instruction. So this instruction replaces the conditional instruction that we saw just now. Okay, remember that here we saw the ADDNE instruction. And this is add when not equal. So that is conditional instruction or conditional execution that exists on ARM32. So on Cortex with thumb2 instruction set, you don't have that. So it is replaced by the IT instruction. So the if-then block emulates the conditional instruction, but it works only on blocks of 4 instructions, not on every instruction, but only after it's preceded. If you put the IT instruction in front of the 4 instructions. Okay, so typically instruction typically you will use an instruction that updates the status register, and then you follow that by an IT instruction in the form of ITXYZ. Okay, so that's few types here. Okay, you can have IT, ITT, ITE, ITTT, and so on. Okay, so this is for the 4 instructions that follows the IT instruction. So let's see one example here. Okay, for the ARM, let's say you want to do. I think this one is if R1 is greater than R0, you subtract R0 minus R1. If R0 is less than R1, which give you a minus result, you subtract, you do R0 minus R1 minus R0. Okay, so on the ARM, each instruction is 4 bytes, always 4 bytes. There's 3 instructions here, so total is 12 bytes. In thumb2, you do the compare as usual, and then there's the ITE PL, okay, ITE plus. So basically, this is an if then else, and if true, you execute the first subtract. If false, you execute the second subtract. So the sub PL and sub MI here looks the same as the original ARM, but because it's in thumb2 or in Cortex, you must have the ITE in front. So because there's only 2 instructions that is conditional, so you put only ITE. There can be up to 4 instructions, so you can have after the IT, you can have 3 more characters here. There's after the IT, there's only E. Okay, let's go back a bit. You can see here, you can have IT, ITT, ITE. So ITTT, so you can have 2, 1 instruction, 2 instructions, 3 instructions, up to 4 instructions. So for example, the last one, ITEEE. So that means the first instruction is executed when it's true, and the remaining 3 is executed when it's false. So here we have ITTEE, okay? So and then we have the LT here, so that means the condition to be checked is the less than. So that one must be the same set used in the true set. Okay, so for example here we have ITTEE. So 2 instructions to be executed when the less than is true, and 2 more when the less than is false. So subtract less than, LSR less than, and then we have the subtract greater than or equal, and LSR greater than or equal. So you must also choose the correct instruction that corresponds to the opposite of the less than. The second example here, we have only 2 instructions to be conditionally executed. So compare R0 with 10. If true, add 2. If false, add 3. So we have ITE only, and then we are going to do the conditional on the IEQ code. Okay. So then we must have ADDEQ, add when equal. Okay. When R0 equal to 10, do the add. What to add? R1 is R2. And if not equal, or the false set is the add R1 with 3. So if you use normal assembler or without the conditional, you will have compare, price equal, price less than, subtract, and so on. There's a lot more instructions here. And if you use the 32-bit ARM, you compare, and then you subtract, and subtract. So if you use the Cortex assembler, what happens is just put ITE here, right? So same, almost the same like the ARM assembler, but you have the ITE in the middle. So example, let's see actually, right? Just put ITE there, but select the first code here. If it's true, subtract. If it's true, subtract. If it's plus, subtract. So you put S sub PL here. So here you can put ITE GT, and it becomes the Cortex version. Okay, so that's it for the IT instruction. Here there's no IT instruction because this is a full 32-bit ARM. Okay, and then we go to the stack, which is very useful that part of any computer. Okay. So stack is a last in first out storage. It is managed RAM because the RAM is controlled by a special register. So as we've seen yesterday, if you push data, you put that more data on the stack, and if you pop, you will to move data. And this diagram is wrong actually, right? So if you push data on the arm, actually, wait a minute, is it wrong or not? I think this is okay. Okay, so when you push data, you will grow towards 0. Check whether the diagram is using for proper or wrong arm convention. Yes, so you can use the stack to swap values. Okay, for example, here we push R4, push R5, and then we pop R4, then pop R5. Okay, so after the first push, the stack here contains AA, because AA comes from the R4. Okay, and then we push some more, we get BBCC on top of it. And when we do the pop, the top of the stack, which is BBCC, gets loaded into R4, and then we pop again to R5, and R5 gets 00AA. So the end result is the contents are swapped. Okay, so this is the original value, the final value. You can see the contents swapped. Okay, you can also use it to preserve value. If you want to preserve values, you can. This one is normally used in the subroutine. Okay, so here you do something which erases a stack to manage some registers, right? So before you modify the register for temporarily, push on the stack first, and then you can do whatever you like. And then before you come back to the main program, you want to preserve the register, but you can preserve the register by popping. Okay, so where is the stack? Okay, so in C program, the code is somewhere here in low memory. Okay, this is the machine language comes here, and then there's the initialized data. For example, here you have something like this, right? This is initialized data because you have initial value there, and then we have uninitialized data. Okay, so this is outside the function also. For example, you have integer k, and then you put it outside. Okay, if you put it outside, then it will be here. But because you don't put anything after k, so this is uninitialized. Anything inside the function here goes to the stack or the heap. Okay. So the code segment, also known as the text segment, contains executable instructions and they reside in the flash. So this one is flash, and this is probably also a flash. Okay. And then some of this gets copied to RAM. Okay, so this one is RAM. Okay, the initial data will get copied to RAM when you start the program. Okay, so the uninitialized data looks like the normal data, but the way you want to know is it's outside. Okay, I think I mentioned I jump the gun. Okay, so this is how you initialize it, or you can also put uninitialized data in a function by giving it the static. Okay, so you have like parity, something like a function, any function, and then here you put static function. So static here means it will be preserved even after you get out from the program, from the function. Anything that is not labeled static will be destroyed because they allocated in the stack. Okay, and then after this program, okay, this is like when you have a program, this is quote unquote program. This is the data that is being loaded into memory by the loader. Okay, so the loader will initialize all this and then it will start executing. So when during execution, you will have access to more memory, okay, instead of just the original data in the disk, for example. Okay, so There's the heap, which grows that way, and then there's a stack which grows this way. So the heap is normally allocate the data then normally allocated by the function malloc on alloc and release by free. So these three functions in C manages the data in heap. For the stack, the management is by push and pop and also by subroutine function, subroutine calls. So rules for stack usage, the stack should always be balanced. That means you must have equal number of push and pop, then you can balance. Too many pushes cause overflow, even one too many push will crash, and also too many pops will cause underflow. So if you push 10 times, make sure you also pop 10 times. So that's stack management. And then we go to the subroutine. Okay, what is a subroutine? Is a code that performs a specific task, also called a method, procedure, or function. The benefits of subroutine, modular, okay, modular program. So that means you can reduce code duplication, you can do code reuse, and you because of modular, because it's modular, you can divide the work among multiple engineers. So when you want to call a subroutine, you jump to the basically you jump there and then you come back. So SOP, the caller is suspended. Okay, normally is the main is the caller. Main is always a caller, right? So let's say it goes to printf. So the main is suspended, control hands over. Okay, hands over control the callee. So now goes to the printf function. So the callee is the printf. So the callee performs the required task like such as printing, and then when it's finished, the callee returns control to the caller. And the subroutine can call each other. So maybe printf will maybe it will call something which the main program cannot see. And you can also have subroutine calling itself. So this is called a recursive subroutine. And subroutine meditative. Okay, so in C, whenever you have that function, okay, so that means the return value is integer. So this is the most common. But you may have a function that doesn't return a value, so you put void. If you put void there, then you don't have a return keyword here. If you have integer, there must be a return keyword inside the subroutine somewhere. But for void, there should not be a return. Actually, it's wrong to have a return keyword. So in assembly language, the function call is done by the BL instruction, and the link register stores the next instruction here. Okay, so this next instruction is stored in the LR. The address of the instruction is stored in LR. And then when you after the jump, then the subroutine is executed, and when finished, we execute the BXLR, which basically copies the link register back to the PC. Okay, so you can have move PC, LR, BXLR, actually you pop. So it's also possible to combine pop with return from a subroutine. But actually before the Cortex, there's a difference between move PC, LR and BXLR. But because the Cortex M4 is permanently tab mode, so both instructions are equivalent. Okay. Okay. So now we go to the topic of leaf subroutines. So leaf subroutines are subroutines that do not call other subroutines. So let's say you have a new program, and there's a function that it calls and the function doesn't call anything else. So that is a leaf subroutine. Or you can also have a subroutine that calls another subroutine. So this function is not a leaf subroutine, but the other one is a leaf one. And then you can also have a function calling a leaf subroutine. So if you have a leaf subroutine, you can use LR to return. But if you are not a leaf subroutine, you must save the link register on the stack before you jump to the list subroutine. Okay, so when we want to go to a subroutine, you must know where is the entry point, what are the parameters, what are the return values, and where are the storage or temporary storage uh, available. Okay, some subroutines needs a lot of temporary storage, so you need to allocate some memory for that. For others, maybe you just use the available registers. So when you want to pass a parameter to a subroutine, you can go to the register or to the stack, or also through the global memory. So the fastest is by using registers, but there's a limited number of registers only. So you can also use the stack for passing parameter, and also you can use global memory. So global memory means there's a memory location that is known to both the caller and the callee. So this one, the global memory method is probably easy, but it locks you to fixed addresses. So you must use the same address, and if you have to change the address, you have to make sure all the functions knows about it. Okay, so because we want to be able to call assembly language from C, kind of protocol or convention that needs to be followed. So the ARM architecture has what's called the AAPCS that determines how you can pass parameters around. So there are this list. Okay, there's this list of registers. So these registers have different groups. Okay, so R0 to R3, they are the argument register. Okay, so if you have only up to 4 arguments to pass to the subroutine, these are the registers that will be the target, the one that you will use to pass parameter from the caller to the callee. If you if you need more, then you will need to use a stack. And then there is the variable register. Okay, so v1 to v5, this is for internal use by the function. And then there's other registers that maybe, okay, there's also v7, v8 here. So there's actually a total of 8 registers that you can use for as a scratch pad. Here, v6 is special. Try to not use it because it's have a special has other purposes besides just a variable register. And then R12 is not strictly defined by hardware, right? Because like PCLR and SP is locked by hardware, but IP here is not determined by hardware, but it's by convention. So this is an intra-procedure call, meaning that if you have a function calling another function, then you have to worry about this. If you just want to go to a leave function, no need to know. So we go to the now what we're going to do is go for the simple ones, passing parameters using just these 4 registers. Okay, so this is one example. Okay, so this is your main, and the main call bar. Okay. Main calls bar, and then after finishing, goes back here. So what bar does is to multiply by 5. Okay, so basically, if you write this in C, it will be like this. It will be here, bar, and then parameter is integer x, then just say return x times 5. Okay, so it needs input value, which is R0, and it also will return the value in R0. So since both you have only one parameter, you can only use the R0 and modify it and then use it to return. So what we have here is we calculate 5R0 and then put it back into R0 and then go back. So the return value is in R0. So when you have return here, when you return something, okay, this value is in R0, and the type is integer. So this is the most common. Okay, if you have Linux, you can try to do this, and you will end up with actually two files, and when you run, you will calculate the proper value. Okay, actually, we can try this. Okay, we have this, right? So let's see what happens. Here, bar, 5. Okay, so actually this fake, right? The scan is fake there, and y equal to bar. Okay, compile this. Go to address 234. Okay, see this? The bar function is the same as the one I predicted. Okay, so this is bar add R0, 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 LSR to BXLR, but it's not called. Okay, so if you can look at the main program here, first it goes to the scan function. Okay, there's a BL scanf. Okay, so goes to the scanf function to get a return value, and the return value for scanf is some in R1. Okay, then it just calculate the R1 times 5. So why is it R1? Is because when you go scanf, and when you do scanf, there's two parameters. So this add x is in R0. This one is in R0. This one is in R1. So the return value is in R1. So R1 gets multiplied by 5, and then before you go to print, the value that was multiplied by 5 will become y, and that goes to R1. So it didn't change anything because R1 already contains the number that you want to print. Then you need to put you need to initialize R0 with the string. Okay, because when you want to print, you need to have a string. So this string is prepared by these two instructions, the move W and move T. So then it will BL to print F, okay, with the R1 and R0 containing the necessary parameters. And lastly, okay, we can skip this this move R0 and SP, but lastly we have the pop. Okay, so this pop is written to the operating system from the main program. Okay, so I did mention just now, right? We can use BXLR, we can use move PC command R, also you can pop. So when you pop to PC, so whatever is on top of the stack gets loaded into PC. So another example, here you have a few variables here. We add the 4 numbers and divide by 4. So when we divide by 4, we just shift 2 places to the right. So this is really short. Okay, that's what it do. That's what it's supposed to do, and quickly get out. Okay, so this is some rules when using subroutines. Okay, the no damage paradigm. If not using register to parameter if not using the register to pass parameter, the subroutine are not supposed to simply touch any other registers. Okay. So in other words, the contents of R0 and R12 should be the same before and after calling subroutine, except for R0. Okay, R0 is the register for needed to return a value. Of course, R0, if it's not needed, then R0 should also be the same. Okay, so because R3 and to R15 are special purpose, we will ignore those. So let's say you want to use R4 and R5 for temporary as a temporary data area during the calculation. So you push first. Okay, just use this syntax: push R4 to R5 and R5, and then pop R4 to R5. And we don't have to worry about the ordering. Okay, so if you put R4 to R5, it's okay because the pop and push when they put multiple registers using a single instruction, they always use the same sequence. So doesn't matter if you put the sequence wrong in the parameter list here, it will be always converted to the same instruction in shell language. Okay, so yeah, push first, then you can do whatever you like to the register that you have pushed, then restore to the old value and return to the caller. So if I have a nested subroutine, which is a bit more advanced than the leaf subroutine, okay, so to call, you just do L like normal, but you need to push the registers that you want to save, like here. Okay, if you want to need to save R4, R5, okay, then you also need to save LR. Okay, the LR must be included in the list. So the link register will also be put on the stack. And then you branch like normal to the new subroutine. And then when you pop, make sure you pop with the PC. So the link register magically is transferred to the PC. So by doing this, you will return back to the main program. So that's the trick lah. So minimal nesting. Okay, so this is quite a simple example. I want to go to this register full subroutine. I want to use R4 as a scratchpad, temporary storage area. I want to preserve it. So I push R4 and I push a link register as soon as I enter the subroutine. And then this subroutine calls list subroutine. So because it's a list subroutine, you don't need to save anything. At the end of this, do BXLR, and inside the middle subroutine, you do pop R4, PC. Okay, so you do know whether you are inside a leaf or not a list subroutine, because you know what are the registers that you need to use. So you do know this lah. So if it's not necessary, you don't do the push and pop. Moment you need to call another subroutine, then you must at least push the link register. Okay, maybe the R4 is not necessary, but the link register must be pushed, and then when you pop, you just pop the PC. So this is what happens here, right? Here we have the pop PC because it doesn't need to save any registers except for the link register, since the main program goes to the scanf and also the printf function. So it needs to save the link register. So if you go investigate here, you can see here the main program does push the LR, and then it does some manipulation with the stack because you need to save data on the stack. So this one is a bit advanced, so to be able to allocate storage on the stack if the register is not enough. But we don't see that much. Okay, so here we also see the stack being accessed, and here the stack pointer is being reset. So normally we try to avoid using stack pointer. So avoid crashing, but the compiler knows better. So when we see the code, we should be able to read it, but when you are writing assembly, you try not to use the stack pointer. So going deeper, right? So variables that are inside the function are called automatic variables. They are stored in registers if variables, stored in registers if available. List routines with 4 registers are simplest. And don't use more than 4 unless really necessary. And if you need more than 4, that is when you need to use a stack. So then you have to understand more. So that one we have it in the last year's notes and the 2, 3 years, 5 years previous, but we remove, okay, because our uh, team is don't get we were not going to write very complicated subroutines, and we are going to write only leaf subroutines. So don't worry about stack. Okay. Lastly, we have this topic called CMCs, right? So in the ARM environment, there is something called there's a library that is already provided by ARM. So this is called the CMCs. There's a lot of things available that you can directly use without having to write your own subroutines. So this CMCs not just provide the subroutine, but they also provide standard conventions to access the register, the exceptions, the names. Okay, when you mention CMCs, also refer to using a standardized name, standardized system initialization, and then standardized name for the clock, and also a standardized C structure. Okay, when you write complex C code, we use structure, and the C structure is also standardized among vendors. So CMC is somewhere here. So when you write your code, you you do need to use some core peripheral functions and also device peripheral functions. So some of these are standardized by company, some of them are standardized by ARM. Okay, so the core peripheral functions are the core peripherals are standardized at the ARM level. Okay, but the device peripherals may be standardized by the manufacturer. So, for example, for STM32, many of the peripherals are the same because they come from the same company. But if you choose to use ARM from another company, the registers will look different because those are the external peripherals that are not defined by ARM. So using the CMCs, you can access all these components. And also, this is the standardized way of using functions. And also CMCs has provide, this is quite an old diagram. And the current CMCs has extra functions for DSP and also for AI. So for those of you who are thinking of doing a project, you should target to use the DSP, CMCs DSP or CMC CNN. Okay. So simply go to, if you're not sure what I'm talking about, just go to CMCs DSP. That's 141,000 results. Yeah, okay, what is it? What is it used for? Okay, so if you can prove that you're going to use this, no problem, your proposal will be accepted. Or you can do this, CMC-CNN, also no problem. Okay, there's a lot of tutorials here, definitely okay, but there's no CMCs for GPIP, I think. So it doesn't say anything. But there's CMCs DAP, this is for debugging. But if you are going to use TCP IP, you can use the LWIP, lightweight IP. Okay, so this is not from the CMC standard, but should be usable. Okay, so make sure your proposal mentions which of these CMC CNN, CMC DSP, or the LWIP. Either one. And easy for me to decide, easy for me to, easy for you to decide. You don't have to worry about me rejecting your proposal. So that's that is the simplest way of going around whether your project is okay or not. Okay, so for CMCs, among one of the things that is standardized is to standardize the C coding convention. Okay, so there's many ways to create C that breaks or C code that uh, give you errors that is not very clear, so subtle errors. So the MISRA C is a coding guideline that avoids this C that is prone to error. So the purpose of the MISRA C is to reduce errors when you write unambiguous C code. Okay, not like the one I gave you in the quiz yesterday, like if alpha equals 0, that is this type of code. So in MISRA C, that kind of code is not allowed. Okay, so there is a lot of rules here in the MISRA C guideline. So this is the foundation of CMC. So the C itself is part of the thing that the CMC try to standardize. And then for the variable types, instead of using integer or character or short, we try to use integer 32 underscore t. This is the standard data type for writing CMC's programs. So here, in our example here, I use integer. So this is not preferred actually, because this is not this is not MISRA compatible. So if you want to make it MISRA compatible, you should include stdint page in front, and then maybe because I haven't tested this. Let's see what happens. Try to compile. Yep, okay, no problem. Okay, so the thing is, when you are writing embedded code, you don't want unambiguity in the integer size. Okay, because integer can be 16 bit, 32 bit, 64 bit. By using uint 32 underscore t, the size is always known because we see 32 there. Okay, so to be able to use this keyword, you need to include stdint. So just put that on top of your program, and after that, every time you see int, convert that to uint 32 underscore t. So the others you can also access using can refer to this table. All right. So conclusion, C or assembler. Okay. So try to do everything in C. Use a profiler to find where is the bottleneck and convert the performance critical section in assembler. And using a linker, you combine all that together and will create a single executable. Okay, so other things that are guidelines in programming, use of floating point is to be avoided as much as possible. Okay, so most ARMs do not have floating point units, including your STM32 Cortex M4. So I don't know about the black pill, but the one on the Nucleo does have floating point. Okay, F446 have floating point. Not sure about the black pill. Anyway, we don't need floating point for most of our projects. So if you're going to use floating point, you can also you can justify that in your project proposal. So because floating point is like such a special thing, okay, and it's not covered in the syllabus. Last time it was there, but then we didn't have time to use floating point. So if you can justify that you need to use floating point in your code, that one is also acceptable as the reason why you need this 32-bit processor. Okay. Next is division. Most ARM have no native division, no native divide instruction. So if you have to divide, and in software it's very slow. It can be up to 100 times slower. So if possible, try to divide by powers of 2. Then the compiler will realize that and try to divide by power of 2, and it will convert to shift. But if you divide by some other numbers, it will use divide, which can be slow. Okay, let's try this. Okay, let's do x divided by 5. What happened? Compile this. Okay, what happens if we divide by 5? It uses the multiply, okay, and then it does shift. Okay, so this one we have to study what it tries to do. Okay, there is a number here. First, it loads R3 with a funny number here, CCCD, CCCC. So it looks like a negative number here, big negative number. Put into R3 and then multiply with that number, and then do a shift. So the combination here is the magic number that it uses to avoid using the divide instruction. So multiply and shift. So of course, you put a different number, you will generate a different code. Okay, let's try 100. See what happens. Okay, 100. Let's see, how does it divide by 100? Same thing. If move something into R3 and then multiply and then shift. So don't ask me. Okay, this one I have no knowledge how it computes these numbers. Okay, these numbers are derived from in combination with the shift, and then the shift here is times 5. See, shift it shifts 5 times. Combined with the big number here, that is equivalent to divide by 100. So all the tricks that compiler does to avoid using the divide instruction, or because there's no divide instruction. Then try to avoid underlined data access, because if you have underlined data, the performance will be slow. Okay, so there's a list of videos to watch, and I think that's it for this morning. So I'm open to questions about the project proposal. Okay. Okay, some of you not clear what is acceptable and what is not. Okay, so any questions? Okay, so I will extend the milestone by 1 week. That's it. Okay, so
one quick question.
yeah.
So, say right, milestone 2, you say you want to upgrade that was existed before, but then just use the microcontroller, right?
Not that
So,
easy. Not that easy. I mentioned there, not that easy. You must justify that it is difficult enough. After you upgrade, it's difficult enough that you cannot solve it using 8-bit anymore.
okay,
The reason is because maybe in 8-bit you have a problem, a performance problem, then that's why you need to 32 bits. So you have to justify why you want to use this. You have, okay, right now is the purpose of the proposal is so that you understand the capability of 32-bit processor, not just treat it as just another microprocessor, which you can solve using a cheaper version, cheaper method. Okay, so when you want to spend money to buy a powerful processor, better be worth the money you pay lah. So that's the idea.
understand. Okay.
Okay. So that's like, I think I've given you the hints. You can use CMC's AI, CMC CNN for the AI, or you can use STM Cube AI back function, either one. Maybe I better write it down in the our Jamboard lah. Jamboard yesterday. That was our Jamboard yesterday. Anybody got the link? I think I lost it. Yeah, this one, right? Yes, I just put something here because easier than just talking, or clearer lah. If I just talk, then it may miss something. I can open it. Nice. Okay. On this one, okay. So for me, it's easy to decide. Easy to sure to need 32 bits. Okay. These are the complex things. Okay. One makes it easy for me to decide. Okay. Just mention CMCs and or CMCs SP. Or this one I'm not sure about the exact name, but it's I think STM Cube. Then floating point. Okay. But for floating point, you have to go deeper to the algorithm and tell me where is the algorithm that you need to use floating point. One, show where is needed. Why you need floating point? Because floating point definitely 32 bits, right? And the one is the RTOS. Okay. So for this one, not 32 bit, but it's also okay. So if you use free RTOS, but you must specify the complexity. If it's too simple and just simply want to use free RTOS, maybe not so good. So at least 2 or 3. Let's say at least 2 or 3 simultaneous tasks. So in this case, you do need free RTOS or RTOS. If only 2, maybe you can just get by using normal one and interrupt. Okay, so for 2 tasks, for running two things at the same time in a microcontroller, you just need to use interrupts. So you don't need RTOS, but if you have yeah, 6 June, okay, yeah. Yeah, 2 things I need to note here. The new deadline, 6/6, no extension. And one more thing, yeah, the LWIP, lightweight IP plus also this one is quite maybe I skip this one. So if you use the IP, then you will get lenience some slack lah. Okay. Use WLP, then cut some slack on the basically if you use the IP for IoT, you still need to use any one of these 5. Okay, so basically if you just use any of these 5, you don't need to use IP lah. For example, you use 3 RTOS and then maybe 2 tasks, then okay lah. 3 RTOS plus LDIP, then okay. Definitely you need 32-bit processor for that. Okay, so I hope it's clear. What I don't want is, for example, some people, okay, uh, just do some simple switch and LED, and that's it for the 32-bit processor. So that's not enough. Maybe is I will ask you something like that in a final or in a quiz, but that is because there's no time in a test to ask everything. But in an assignment, it will be uh, more complex than that. Right. So if there's nothing else, we'll adjourn for now and continue at 2 o'clock. All right.